Welcome to my talk, New Approaches to Reduce Alert Noise. And when you visited the talk of Miko this morning at 10, he asked the question of what is AIOps and was making a little bit of fun of it. And I'm glad that he accepted my talk because my proposal had AIOps in the title. Now I removed it. I think we'll see some of AIOps today. So I'm going to be talking about how to leverage AI and LLMs. It will be somewhat related to the talk of Marcin that we just saw. But I will present a very specific use case, how to leverage LLMs for the task of alert noise, alert fatigue. My name is Birol. I am the CEO and co-founder of iAlert. And iAlert is a SaaS company based in Germany. A company, we provide a software platform for incident response. And as of today, we cover everything around incident response, and this includes alerting, on-call management, status pages, and incident communication. And then being a central platform for critical events, we sit on top of many observability tools. Some of them I was able to meet here. So we partner with observability tools and monitoring tools and ITSM tools. And we serve as the central dispatcher for critical events, and we essentially connect people with the system. At the end, we have people on call. They need to receive the information outside of business hours, and we're the ones, or our software is the one who would give you a call at 3 a.m. that your system is not working. And today we are very proud to serve like large companies and small companies alike, including Rewe, including IKEA, and including also some large managed service providers, entity data, of hopefully whom you had the chance to visit Jorge's talk. To set the stage, I would like to just show you a screenshot of one of our customers. They were able to achieve these results after 2 weeks of enabling or using intelligent alert grouping, which I will be talking about today. So after 2 weeks, they were able to reduce alert volume by 93%, and they were able to improve response time by over 4 hours. So they saved over 4 hours in response time. And as every minute in saved response time directly impacts MTTR, and every minute in improved MTTR directly impacts service uptime. And service uptime for you as SREs is one of the most important metrics, right? But before I talk about reducing alert noise, I just wanted to give you a quick overview of the other areas in incident management or incident response where you can make use of AI and LLMs. We think with these technological innovations, some of them are overhyped, and some of them are just like technology looking for a problem to solve. But with AI and LLMs, I think the overlap between you have a problem and a potential solution is very high. And so there's a really good balance between the value that you're getting. And we're using today AI across multiple areas. And when we look at AI, we think of how can we improve the user experience? How can we, and hopefully in a way that makes the AI invisible to the user. And now let me talk about 2 or 3 use cases, just in case you're interested, and feel free to talk to me after the conference if you want to learn more. So one is using AI for on-call scheduling. On-call scheduling can be sometimes a complex task, especially if you have a distributed team and you would like to create follow-the-sun models. We've implemented a chat interface to create on-call schedules where you just talk to the AI and say, hey, I have 2 teams. One of them is in London, one of them is in the US. Create a follow-the-sun schedule for me. And then the AI walks you through the process. Another area is incident communications. Yesterday, there was a talk, and the speaker was saying something along the lines of, most people in tech, they don't like to write, especially if it's for someone else to be read. And this also applies to incidents. When you need to communicate incidents to external people, to maybe your customers or to stakeholders within the company, and this message will appear on a status page, and you're in the middle of firefighting, you don't want to spend too much time on crafting that message. And that's also something where we think we've integrated this beautifully into the interface. You just throw in a few words, could be like API is down, payment services are all affected, next update in 30 minutes. And then we'll craft a beautiful message, select all the services that are affected, and just shoot out the communication. So instead of spending maybe 5 minutes, you spend just 30 seconds on the incident comms. And another area where we've been working is post-incident reviews or post-mortem analysis. This is an area where we think it's almost irresponsible not to use, because the way post-mortem meetings work is most of the time goes into preparing for these meetings. You have to look at large amount of data. Maybe there was, but probably if it's a major incident, usually you have war rooms where many people gather and they collect like they have a conversation, they agree on actions, and then you can have just AI to create an 80% version of your post-mortem document with an incident timeline, with a description of business impact, with a description of anything that was agreed in the war room chat, and then invest the time in the actual valuable tasks of post-mortems, which are how can we learn from this major incident. But today, or now, I will be talking about how to leverage AI for reducing alert noise. And that's a problem many of us face, right? Being flooded with many irrelevant alerts or many alerts that are related to the same underlying cause. And I'm going to just walk you through a few basic concepts that are important to understand on how we've implemented this. At the end, maybe you can also implement this. Let's first talk about what do I mean by alert grouping or alert deduplication. Alert deduplication is the process of identifying multiple alerts that are related to the same issue and just grouping them in one alert. So instead of having 10 alerts, you just have one alert since it's related to the same issue. And this will save you time, it doesn't overwhelm you. And sometimes you have massive floodings, like 10, 20, 30, hundreds of alerts in a very short period of time. And I'm going to be talking about an approach called Embeddings similarity search. If you visit the previous talk, you know what an embedding is, or what a vector embedding is. But nonetheless, I'm going to walk you through all these concepts, and then I'll describe how we've implemented this. So what's a vector embedding? A vector embedding is a mathematical representation of a piece of data in a high-dimensional space. So when I was looking at your chart, Marcin, 2 dimensions is really 2 dimensions. But of course, for illustration purposes, you want to make it very easy. But usually, like these vectors, they contain like hundreds or thousands of numbers. So you have a piece of data, could be an image, could be a document, could be a word. And this piece of data is translated into a series of numbers. Potentially, again, depending on the dimension of the model, thousands of numbers. To give you an example, when you use, for example, like ChatGPT, when you write a prompt, that prompt is first translated into a vector first. And this is like paramount in almost all the LLM use cases. We always, if you look at the parameters files, there are a series of numbers. But the question is, what's the algorithm for having a piece of data, in our case, an alert, and transforming that to a series of numbers? And this is where like the magic comes in. We're going to use an embedding model. And an embedding model is a special type of pre-trained machine learning model that was trained on like specific data, and it's capable of representing specific data types. For example, you can have these large embedding models that were trained on general textual data. That includes large data sets such as Wikipedia, but also data sets, in our case, for example, that were also data sets from Stack Overflow were used. So a large variety of data, but you can also train these embedding models on like different data types such as graphics. And we don't train them ourselves, so we use one of those existing open source embedding models that are available that were pre-trained. So we don't actually do the training ourselves. And the result is, again, if you look at the example, if you have a sentence like this, the output is always a series of numbers, potentially thousands of numbers, depending on the number of dimensions the underlying model has. Okay, now given these 2 concepts, we know what a vector embedding is, and we know how to turn a piece of data into a vector embedding, which is the embedding model. How are we going to use this for alert deduplication? In a nutshell, we will transform all alerts into vectors, and then we will perform a similarity search on top of these vectors. And then let me walk you through all the steps. The first step is we normalize the data. And for us, it's a given because we are a central alert management platform. We have a common alerting format for alerts across all the monitoring tools. So there is a format for alerts that works across all the tools, all the observability tools, and all the ITSM tools that we integrate with. And in the second step, you would also clean the data. And cleaning involves like removing any bits and pieces that are not relevant for the task at hand, which is deduplication. For example, if you look at IDs, timestamps that are unique to each alert, you just remove them. And this also includes any like structural data that is specific for the format. For example, if you represent your alerts as in form of JSON document, you would remove all the syntactic elements of JSON. So the end result is just plain text. You have an alert that is reduced to the basic elements of what the actual alert means, and you just have plain text. And these alerts are stored in before you have pre-processed the alerts. Now you need to choose a text embedding model. You can also use one of the available text embedding models from OpenAPI. You just call an API and then it gives you a vector. But of course, for us, and probably also for you, this is a critical flow where you have potentially very high traffic and you don't want to rely on an external API, right? Because you cannot afford the latency because it's a high throughput use case. And that's also why we use offline open source text embedding models. And you store these vectors in a vector database. Ideally, it's an optional step, but these vector databases, they are optimized to manage, to store and manage vectors, and you can very efficiently perform queries on them, such as a similarity search. And a similarity search is nothing else but you have a distance metric. Usually it's like something like a cosine distance, where you just calculate the distance between two vectors. And this returns a number between 0 and 1. The greater that number is, that means the closer the vectors are, which in turn means both vectors, they capture the same semantics. Okay, and the last step would be to implement the deduplication logic, which again is just a simple comparison operation. You have, for every incoming alert, you just search for similar alerts and you have a threshold. Let's say it's like 0.8. Everything that's above that threshold you consider as a duplicate and you group it into the existing alert. And the main advantage of this approach is it captures the semantic understanding. So for two alerts to be considered identical, they don't have to match on a textual level. So usually when we apply traditional alert grouping techniques, we either rely on a time window. Let's say you have a grouping window of 5 minutes and everything within 5 minutes I always consolidate, or you rely on a common key that is, let's say it could be a service key, a host key, that's a deduplication key, but you're relying on something specific, or you can just look at the textual similarities. But in our case, we're capturing the semantics. So even if two alerts are different on a textual level, they can still mean the same, or they can still be related to the same root cause and can be grouped together. Of course, there are a few, and this is also like a very scalable approach because we have very low latency. We host the model on our own. We don't actually need a large language model the way, for example, Martin was presenting it. This is not an RAG use case. We're just using text embedding models to store the vectors. And we don't talk to ChatGPT or whatsoever. So it's a very scalable approach. And what you have to consider is pick the right text embedding model, do some threshold tuning, and also gather some feedback. In our case, we provide a simple thumbs up, thumbs down whenever an alert was grouped, where someone can say, okay, this was incorrectly grouped or not correctly grouped, and then you can use that information for fine-tuning purposes. I'm going to show you, I prepared a live demo, and I'm going to show you the effectiveness of this approach. Allow me to sip some water. Okay, here at the top, I have an overview of all the open alerts. So right now, there are no open alerts. And in the bottom, I have Postman, where I'll just shoot a few alerts. We have a very simple API for this. And let me start with a made-up alert that says coffee machine on floor 2 needs a maintenance. That's a very simple alert. And of course, because this is the first alert, it will create a new alert, right? Now let's move on. Let me send another event and change the description of the text. So this time I'm going to say, alert, coffee machine on floor 2 is taking a coffee break. It's still similar. It's not exactly the same. Let's see what happens if we submit this event. So I'm going to refresh the page, and you see no new alert was created. So the alert was aggregated. We can see here in this indicator, there are 2 events that were aggregated under this alert. If we look at the alert, we can see it consists of actually two alerts that were sent, but we didn't create an additional page whatsoever. Okay, let's be a little bit more, or let's try to be funny and submit another alert that says no Java from the Java machine. Floor 2 coffee maker is down. Let's see what happens. It says 3, right? Yeah. So this alert, again, was grouped. We didn't create a new alert because it's still the same underlying problem. We're still talking about the coffee machine. Now let's try a counterexample. Let's say we're not talking about the coffee machine, we're talking about the water cooler. The water cooler on floor 2 is broken. What we would expect, of course, is that it creates a new alert, right? Because it's a different problem. I've just submitted this event, and it creates a new alert because semantically it's a different thing. That's why we created a new alert. There might be a different team responsible for the water cooler. Now you might think these are like not real examples. My alerts, they are not about coffee machines. They are not about water coolers. I have like CPUs, hard drives, pods failing. So let's try more real world examples. Let's assume we have an alert where the hard drive is full, or the hard drive is reaching its capacity. And we're going to just phrase it like this: the hard drive is full. Of course, this is the first alert in this regarding the hard drive, therefore it creates a new alert. And let's try rephrasing this to the storage capacity has reached the limit of 90%. In this phrasing, you can see there are no common words between the hard drive is full and the storage capacity has reached the limit of 90%. So there's nothing on a textual level that you would be able to group these two alerts together. So this second alert is also grouped with the first hard drive problem, and we haven't created a new alert. Now let me even go a step further. Now you might think these are just simple sentences. They consist of one sentence. Production data, production alerts, they have like more complex information, the amount of information is more. It's not going to work in production. Okay, I get it. And we've developed this a few months ago, maybe 6 months ago, and we've been observing this. And the next example I'm going to show you is real production level alerts, where we know that these were instances of alert flooding. So what I'm going to do is before I send these production level alerts, and these are going to be like 30 alerts, I'm going to disable this intelligent alert grouping first and see what happens. So I have prepared here a collection in Postman. It takes about 5 seconds to run, and it will trigger 31 alerts. So let's run this collection. Okay, it's finished. So we have just fired 31 alerts and go back to the alert screen. Let me make this full screen. And you can see here, we have actually created 31 alerts. And if you look at all these are like production level alerts with a full payload. They contain detailed messages. And if you just scroll through these alerts, some of them are similar. There's a black box probe failed on an instance. And then we have also very different alerts where RabbitMQ node is down. Now let's try the same again with intelligent alert grouping enabled. So let's go back to the settings of the alert source, enable intelligent alert grouping. And there are two settings that come along with intelligent alert grouping. One is the time window, and the second is the threshold that I was talking about. The threshold is a number between 0 and 1. Just to make this a little bit more concrete, we're providing a preview of what happens when you move the threshold. For example, if I lower the threshold, you can see more alerts are grouped. And if you increase the threshold, fewer alerts are grouped. So let's leave the default setting of 0.05, 0.75. And let me save that again. Go back to alert list. First, resolve all the open alerts. And now, done. Let's run this collection again. So it is now, again, firing 31 alerts against our API. And we now see we don't have 31 open alerts. We have 1, 2, 3, 4, 5 alerts. And are these 5? Yes, 5. No more alerts coming in. Yeah, looks good. And you can see all of the alerts, they refer to completely different things. So some of them, here is a hardware status is not healthy. A RabbitMQ node is down. And we have another system low disk space alert. And I think this was you could see how effective this approach can be. And actually, it's also a no-brainer to activate if you have a fairly sensible grouping window. So let's say you choose a grouping window of 15 minutes. There is not much that can happen if you just try this out, because you know that after 15 minutes, you would discover other alerts as well. And this provides just a basic level of protection for alert flooding and saves you the time and energy of having to go through multiple alerts. And we use this approach in many areas, including, for example, let's say you haven't enabled alert grouping. And after the fact, you end up with 100 open alerts. And every time you resolve an alert, we look for similar alerts and suggest there are other similar alerts from the same category. Would you like to resolve them as well? So it just makes the user experience easier. Okay, that was my presentation and my demo. And I think I'm right on time.